So I'm going to be continuing talking a little bit about optimization today, mostly just going over a few more examples of optimization problems and things like that that we can take a look at. So here is an example that is a little bit different than the ones that we did last time. So let's suppose that I want to ask the following question. Find the point on y equals, let's say, 6 minus 2x closest to the origin. Now, this is not really an immediately obvious problem. It's sort of a geometrically obvious problem, but it's not really obvious in terms of like other stuff. So why is it geometrically obvious? Well, the reason is because the closest distance between a point and a line is via a perpendicular. And so we could solve this by using the perpendicular, but I want to show you how you can solve it by using calculus, because more generally, you may have to solve these problems using calculus. An example where you would have to use calculus: what if instead of minus 2x, what if instead we did like minus 2x squared, so that we're talking about points on a parabola or something? So how are we going to do this? Well, the distance is going to be equal to the square root of x squared plus y squared, because we're talking about the distance to the origin. And that means this is going to be the square root of x squared plus 6 minus 2x squared. So this is going to be the square root of, let's see, when we expand this out, this is going to be 4x squared, so a total of 5x squared, and then we're going to have negative 12x and another negative 12x, so minus 24x, and then we're going to have plus 36. So this is my formula for the distance. And at this point, there's a couple of different ways that we could go about doing this. Probably the easiest thing to do is to say this means that d squared is 5x squared minus 24x plus 36. That means that 2d prime is equal to 10x minus 24. And that means that d prime is going to be equal to 10x minus 24 divided by 2d. Now, the reason why I'm writing this as 2d and not bothering to put anything else in is because I'm really only interested in where this thing is equal to 0. And the distance itself is never equal to 0. So if we set d prime equals 0, this is the same as 10x minus 24 equals 0, and that gives me x equals 24 over 10, which is going to equal 12 over 5. Because I don't actually need to worry about the distance here. I can just multiply both sides by the distance. The problem is I now need to show that this really minimizes the distance. There are two different ways that I can show it minimizes the distance. One method is I can show that the second derivative is positive here, and therefore this is a minimum. But taking the second derivative would be a little bit of a pain. So is there an alternative I can do? Well, the answer is yeah, there is actually an alternative. The alternative is I can notice this is the only critical point. And the other thing that I can notice is that in the limit, as x goes towards plus or minus infinity, d as a function of x also approaches infinity on both sides. So why does that matter? Well, what that means is we have a function that is going off to infinity on both sides, and it's got one critical point in the middle. The only way that that can happen is if that critical point is a minimum. Okay, think about that for a moment. Why is that true? The only way that that can work out is if this comes out to be a minimum. So that means that at x equals 12/5, we really do have a minimum. And then what we can say is, well, that means y is 6 minus 2x. That's going to be 6 minus 24 over 5, which is going to be 6 over 5. So we end up with our point being the point 12 over 5, comma, 6 over 5. Now, if you want to double check to make sure that this really is going to be on a perpendicular with the origin, you can go ahead and do that. But this is how you solve this problem with calculus. Now, like I said, there's a reason why you might want to solve this with calculus. Namely, in some other problems, things might be a little bit more complicated. For instance, let's suppose that instead of that problem, we want to find the point on y equals 1 over x closest to the origin instead. So I will ask you to actually take a minute and see if you can do this problem, and then we'll work through this together. So pause this, see if you can work it out. There's actually a bit of a trick here. There's two different points that both work. So, but I'll give you a minute to check this out and then see what happens. Okay, so the distance here is going to be, once again, square root x squared plus y squared. That's going to be the square root of x squared plus 1 over x squared. So this means d squared equals x squared plus 1 over x squared. So 2d d prime is going to equal 2x minus 2x to the minus 3. Now, if we set this equal to 0, we can start by saying that x equals 0 is not in the domain. So I can multiply through by x minus x to the, or I can multiply through by x to the minus 3. So, well, first of all, maybe we should say d prime is equal to x minus x to the minus 3 divided by d. But if you set this equal to 0, you just have x minus x to the minus 3 is equal to 0. So we get x to the 4th minus 1 is equal to 0. This is going to give me x equals plus or minus 1. Now, can we argue that these minimize? Yes. And the argument is the same as last time, almost. So the argument that these are both minimums is going to come from the fact that in the limit as x approaches 0 from the right or left, the distance function approaches infinity, and in the limit as x approaches plus or minus infinity, the distance function also approaches infinity. So our domain here is split up into two intervals, the x bigger than 0 interval and the x less than 0 interval. But in both cases, we end up with a minimum. So we take our 0 and we split the domain. At x equals 1, this is going to be a local minimum, and at negative 1, we have a local minimum as well. Because our function blows up to infinity around 0, and it also blows up to infinity on both ends. So our critical points have to actually be minimums. And then we just have to check which minimum is smaller. Well, it turns out that for both minimums, the distance is square root of 2. So the closest approach is at 1, 1, and at -1, -1, and the distance there is the square root of 2. But we've shown that it is a minimum in the same sort of way as we did the previous example. So there's another example of an optimization type question. Now you can get more complicated optimization questions as well involving distances. Maybe we want to find the distance to some other sort of point instead of the origin. I chose the origin in both of these examples, but in general, maybe you're trying to find the closest distance to some other point. Or maybe you're trying to do something a little bit different with the distance, who knows. But there's all kinds of things that you can calculate using the distance formula here and optimizing it. Now let's think about a slightly different sort of optimization problem that comes up rather frequently. Let's suppose we want to build a rectangular box with a square base. And let's say the sides and the bottom cost $3 per square foot. And the top costs, let's say, $1 per square foot. And if we need to contain, let's say, 1,000 cubic feet, what is the cheapest cost? Now, do be careful when you look at these questions, okay? Because we're asking here, what is the cheapest cost? Now, another question might ask us, what are the dimensions that minimize the cost? We're going to find that in the process, but my point is, I want you to make sure that you read the question carefully and answer the question that is being asked. Don't just, write down some number and hope for the best. Go for a specific, make sure that you actually understand what they are asking. The next thing is to make sure that we understand the setup. So I'm going to say, let's say that the base is x by x. And then the height of this thing is going to be y. So here is what we can say in terms of the objective and the constraint. The cost of this thing is my objective equation. And the cost is going to be 3x squared plus 3 times 4 times xy plus an additional x squared. So why is that true? Well, it's 3 times x squared for the cost of the bottom. Then I've got 4 sides that are all x by y. For each one of those, it's $3 per square foot. So that gives me 3 times 4 times x times y. Finally, we've got the lid, which is only $1 per square foot, and it has an area of x squared. So that's where I get this formula from, and this is going to give me 4x squared plus 12xy. By the way, why would this be true? Well, maybe what's going on here is the sides and the bottom might need to be made of a special material because, maybe this is like a corrosive liquid that we're going to be storing in here. And so the sides and the bottom need to be made of a special material. But the liquid, splashes the top, but it doesn't really sit against the top. So maybe the top can be made out of something cheaper. And then we have our constraint. So our constraint is going to be that the volume needs to equal 1,000 cubic feet. But it is also equal to x squared times y. And this means that y is equal to 1,000 divided by x squared. So we can rewrite our cost equation as a function of x alone and say c of x is equal to 4x squared plus 12x times 1,000 divided by x squared. And that is going to give me c of x is equal to 4x squared plus 12,000 divided by x. And notice here that x has to be strictly bigger than 0. The other thing to notice here is that as x approaches 0 and as x approaches infinity, the cost approaches infinity in both directions. Because as x gets very, very large, the cost goes up to infinity. And as x gets close to 0, the cost goes up to infinity as well. So this means that if we can show that there is exactly one critical point in here, it will have to be a minimum. So now we can take the derivative of our cost function and we can say c prime of x, this is going to be equal to 8x minus 12,000 x to the minus 2. If I set this equal to 0, I can multiply both sides by x cubed, so I get 8x cubed is equal to 12,000. And that means that x cubed is equal to, let's see, if I take 12 divided by 8, that's 3 halves, so this is 1,500. So x cubed is equal to 1,500. That means x is equal to the cube root of 1,500. And at this point, we take this and we say, well, this has to be a minimum because it is the only critical point, and on both ends of the domain, on both ends of this interval, the cost goes up to infinity. So just like in the previous examples with the distance, I can argue that this really is a minimum. Actually, in this case, it's even easier to see that it is a minimum because we can say, well, look, c double prime of x is going to be equal to 8 plus 24,000 x to the minus 3, which is bigger than 0 for x bigger than 0. So by the second derivative test, this is a minimum as well. So there's actually multiple ways of showing that this really does minimize the cost. And now, to get what is the cost, well, we just take this cube root of 1,500 and we plug it into this expression. So whatever that comes out to be, that is going to be our cost. So the cost evaluated at cube root of 1,500, this is going to be 4 times cube root 1,500 squared plus 12,000 divided by the cube root of 1,500. And I will leave it to you to throw that into a calculator because at this point, it's really just a matter of getting an estimate like that. So there we go. So there's another example of doing this optimization stuff. Now, I'm going to ask you to take a look at a few more optimization questions. For instance, go to Paul's math notes and look at his optimization problems because it's a good idea to get some additional examples of this kind of thing. But I think that takes care of the ones I wanted to show you. So I just thought I would say a few things about an application of this into physics in terms of Snell's law. So I mentioned this last time. but let's think for a moment here about Snell's law and what it says. So Snell's law deals with the following sort of scenario. Suppose that I have two different mediums in which light is going, okay? And the light comes in here like this, and this is a right angle. This angle here is going to be theta 1. And it turns out that when the material changes, the angle is going to change as well. So this is our theta 2. And we want to have two different expressions. We want to have n1 and n2 with the properties that the velocity of light over here is going to be the speed of light in a vacuum divided by n1, and the velocity of light over here is going to be the speed of light in a vacuum divided by n2. There is a reason why we want to end up with this sort of thing going on here. So what we want to do next is we want to consider the following construction. So we're going to call this distance here x, this distance here a, and this distance here b. So assuming that we start here, go through here, come over to here. Then what is the total time going to be that we take? Well, the total time is going to be equal to square root of x squared plus a squared divided by v1 plus the square root of, I forgot to tell you what this distance is here. So this total distance here is going to be L. This will be the square root of b squared plus L minus x squared divided by v2. And what we can do at this point is we can write down the following. So we can say that the total time is going to be equal to, when I simplify this out, it's going to become square root of x squared plus a squared divided by v1 plus square root of b squared plus L squared minus 2lx plus x squared divided by v2. And then what we can do is we can take the derivative of t, the time, with respect to x. And when you do this, you're going to end up with the following. So you end up with x divided by v1 times square root x squared plus a squared plus negative L minus x divided by v2 times the square root of L minus x squared plus b squared. And we're trying to figure out where this is equal to 0 at, because it turns out that Fermat's principle states that light will always take the path that minimizes the time. Now, at this point, what we can notice is that this quantity here, this, if you go back to that picture that unfortunately I had to erase, this is actually the sine of theta 1. And this quantity over here is actually the sine of theta 2. And so what we end up with is that the sine of theta 1 divided by v1 is equal to the sine of theta 2 divided by V2. And usually the way that Snell's law ends up getting written is in terms of that N1 and N2. And so you end up with N1 over C sine theta 1 equals N2 over C sine theta 2, like so. And that's all that Snell's law says. So Snell's law really comes from a minimization problem using Fermat's principle. Now, there are other ways of deriving Snell's law. So you can think about some other ways of getting it because, well, Fermat's principle is not necessarily obvious, but it turns out that there are ways of justifying Fermat's principle. It turns out that essentially what's going on is the light waves have what's called destructive interference in all cases except for the path that extremizes the time. It also turns out it's not really about minimizing the time so much as extremizing it. It's just that the only way to extremize the time of a path is to minimize it. So it turns out that, yeah, you do minimize it, but really what matters is the fact that this derivative is zero. So what matters is that the light follows a path that gives you a critical point. Anyway, yeah, so this is just a derivation from Fermat's principle. Justifying Fermat's principle is a little bit trickier in terms of the theoretical stuff. But I figured I would show you this example, although I will leave it to you as a bit of an exercise to make sure that these derivatives are correct. I figured I would show you because, you know, this does turn out to be a really important kind of idea throughout various applications. And I also wanted to show you this example because, well, for those of you who do have an interest in physics, it turns out that this whole Fermat's principle turns out to kind of generalize massively. So it turns out that in general, all of classical mechanics can be derived from this idea of extremizing certain quantities. Those quantities are known as the action. And it turns out that there is a really good reason from quantum physics why classically this is how things behave. And it comes down to, similarly to the way that you derive Fermat's principle, it turns out that there's destructive interference in all the cases except for those that extremize the action. But unfortunately, in order to study extremizing actions, you actually need to go back to that stuff that I mentioned last time, calculus of variations stuff. So really, this is kind of a plug for why you should be interested in calculus of variations, because it turns out to be really, really useful in physics and also in some other things as well. When we're talking about like all kinds of different modeling things that calculus of variations is useful for. But sort of the simplest case is deriving Snell's law between two different materials like this. All right, so that takes care of, I think, most of what I want to say about optimization. Make sure to look at the other examples in your book and on Paul's math notes, just to make sure that you've got some additional examples to kind of think about. And then we're also going to be taking a quick look at Newton's method of trying to solve equations or approximate solutions to equations this week. So we're not going to spend a tremendous amount of time on that, but it is kind of an interesting thing. The basic idea is that essentially, if you want to solve an equation, if you want to figure out where a function is zero, you can start by doing a linear approximation to the function. And then you figure out where the linear approximation is zero. And then you go back to your original function and you do a linear approximation at that point. And you repeat this process iteratively. And the idea is that you hope that you sort of focus in on the true zero by doing this kind of thing repeatedly. So if you need to estimate where a function is equal to zero, this can be somewhat useful. How useful? Kind of depends upon the situation. Now that we have computers, people have other methods of estimating zeros as well, but it's an interesting thing to look at anyway. So I'm going to end this video here for the moment, and I will talk to you later.